anything that's of extremely, it's not as if it's a very fine line. There are more zones of transition. So this is what fronts exist, where air masses come together and meet. And because these air masses have very different characteristics, the differences between the air masses can create some very interesting situations. So just to kind of make an intro and then lead into the next slide, suppose we have a cold air mass, such as the continental polar air mass, meeting up with a cold dry air mass, such as continental polar, meeting up with a warm, moist maritime tropical air mass. The advancement of the cold air would be represented by what is called a cold front. So the cold front will give us an indication of how far the cold air has advanced, and then we'll have a warm front for the representation of the advancement of the warm air. So here, for example, is our cold front, the front that is shown here in blue with the triangles. So back in here, this is the so-called cold sector. And you can see in this case, it is the consequence of continental Arctic air that has moved in from the Canadian north. It's moved down to very lower latitudes here. My goodness, it's moved right into the US. And so there's a significant amount of cold air that has infiltrated to quite southerly latitudes. So again, here's the progression of the cold air. This is as far as that cold air mass has moved. So back in here is where the cold air is. We call that the cold sector. Down here towards the south, we have a warm, moist air mass, maritime tropical origin, out over the Gulf of Mexico, that's making its way to more northerly latitudes. And you can see where it has made it to is indicated by this line here, CD, where you have the red semicircles that show the advancement of this warm front. So back in here, we have warm air, and air is moving kind of towards the north and east here. This is called the warm sector. And what we've actually got here, what you're actually looking at, is a very typical garden variety middle latitudinal cyclonic system. Okay, a cyclone. So cyclone, I think we've already introduced it here. That's a generic term for a low pressure system. So here, what you're looking at on this graph are contours of constant pressure. So each of these black lines here is an isobar, and any point on that isobar is at the same value, in this case, the 1,028 hectopascal contour interval here. This is from our Canadian edition of the textbook. So the isobars are indeed contoured in hectopascals. If you happen to find data from the US, they tend to use millibars. I think the UK does as well. But under the metric system, these lines here are pressure. So this is basically a weather map. And it starts with taking pressure data from all kinds of stations. Each of these little things here, these dots with these funny looking arrows sticking out of them, each of those is a weather station. And we take data, so weather stations like EMOS. So we take data from weather stations, take the pressure data, and produce a map like this. This is a representation that is called a contour map. And so if you think about elevation in terms of giving you an analogy for this, what you'd be seeing here is kind of a low-lying structure here. This looks like a valley that's been hollowed out. and this looks like a small hill that has been that has risen relative to the background. This represents a region of high pressure, and this represents a region of low pressure. Now, there's a tremendous amount of data on this particular map here. It's easier to see some of the data down here. So here we have 2 weather stations. The dots, how the dots are filled in is actually meaningful. It tells us the amount of cloud cover. There are symbols that might appear to indicate the precipitation type that is observed at the station. So you can see here, for example, some of the stations are reporting that there is light snow falling. And each of the stations, as I mentioned, has this these funny looking arrow things that are sticking out of them. The arrow things that are sticking out are showing us the direction of the wind. So for example, for this station down here, right over the state of Texas, just north of the Gulf, if you were to stand on this dot here, and hopefully you can see my arrow, if you were to stand on this dot here and face towards this arrow, you'd be looking towards the southwest. So you would describe the wind at this station as coming from the southwest. Winds are named according to the direction from which they blow, from which they originate. And so what you can see here is within the warm sector, the winds are fairly consistent in terms of their direction. There may be some variation in direction and even speed, but that's pretty much one of the characteristics. And they're very different from what you observe over here on the other side of the cold front. So this is in the cold sector. So are the temperatures. The temperatures that are shown here, as you can see down here at the bottom, there's a little bit of a legend. You can see that the number above is the air temperature, and the number below is the dew point. Okay, and because this is a Canadian map, I will assume that these temperatures are in Celsius. Believe that is the case. So for example, down here, if I go back to our same little weather station, you can see that the temperature at this weather station, the air temperature is 15 Celsius, the dew point is 10 degrees Celsius, 14 and 9. So the temperatures and dew points are fairly consistent within the warm sector, as they should be, because that is the same air mass. Same thing here as you cross the boundary. The temperatures are relatively consistent within the cold sector, and obviously they get colder as you go to more northerly latitudes. So what this means is that when we, so first of all, the pressure, this is the line, the isobars are lines of constant pressure. This is what's called a contour map. So we are representing in a latitudinal and longitudinal perspective here the variations of pressure. The data for pressure is observed data. Pressure is one of the fundamental atmospheric observables. You know that EMOS, for example, provides us with atmospheric pressure, and we end up with a value from EMOS, and it needs to be corrected so that it is as if it were measured at mean sea level. So just to remind you, right down here, here's the data for EMOS, right? So at EMOS, if you happen to be on the York campus today, the campus, the actual pressure that is measured by EMOS on site right now is 995.0 hectopascals. And then if we correct that so that we get the mean sea level equivalent pressure, we get 1018.2 hectopascals. Okay, so basically this map that I was showing you, or maps like this, are produced by taking data from individual stations like EMOS, collecting them on a regular basis, and then putting them all together on a map representation, and then developing a contour representation. This is something that gets covered a bit in the material. I think it was chapter 8, 9 material where I was talking about pressure and wind. Anyway, so that's the basis for our weather map. That's the primary data that we start with, and then in order to place fronts on a map like this, the first thing we look for are these weird looking bends in the pressure data. So you can see here, there are these little kind of, instead of this being a nice kind of smooth oval or something like that, the existence of the front introduces a little kind of a kink in the isobar pattern. And so this is one of the criterion that is used to locate a front. And when you go through the textbook or the captured lectures, what you'll find out is that that's one of about 5 different criteria. Other things we look for are changes in wind direction. Okay, so down here from southwest, up here from the north, slightly from the northeast. When we see changes in wind direction, that also teases or triggers for us that there is a front that is likely in existence there. We look for changes in temperature, okay? So you can see here in the cold sector, the temperature is somewhere between -8 and -5. In the warm sector, it's more like about +15, +14, so quite a difference in temperature. And we also can look at changes in dew point as well. So we put all of these different things together. We also look at the existence of clouds and precipitation. So basically to infer the location of a front, and that's really important. This is something that an atmospheric scientist, a meteorologist, somebody who focuses on weather would actually, that's part of what they do, is they infer the location of fronts based on various criteria, not just one criterion in isolation, multiple criteria. Now, there's a lot more going on here. And by the way, this is all happening, this scale here, which is kind of like a continental scale, is the so-called synoptic scale. And what's also quite interesting is, of course, you may recall I said that one of the distinguishing characteristics about breezes and even monsoons is that, relatively speaking, they are stationary systems. They have circulation, they have flows that are going on, they don't move around. Cyclones move around. In general, cyclones move from the west towards the east across North America. And as they move, they evolve. Now, one of the things that's also happening as this cyclone is moving is the cold front here, which is marking this advancement of cold air. Cold fronts tend to travel faster than do warm fronts. And so, as you'll learn in the captured lecture material and the material from these chapters in the textbook, what that means is that it's very frequent for a cold front to actually catch up and overtake a warm front. And when they do, other interesting things happen. So that's what you're looking at here. Now, this is quite an interesting diagram because it's actually showing us both the American and the Canadian convention for indicating the place where the cold front has caught up with the warm front. So where the two fronts first meet, we produce what is called an occluded front here. It's shown here in purple, and as you can see, it's got a combination semicircles and the triangles, but they're all pointing in the same direction. So this is the place where the two fronts initially meet. This topic is considered in more detail in all those other resources that I keep referring to. The way that they are indicated in the US is by, if you look at a US weather map, you will see this idea of an occluded front, okay? When you look at a Canadian weather map, you will see what is called trowel, which is shown here. This kind of looks like an axe head or something like that. So this thing is called a trowel. Trowel is an acronym. It stands for Trough of Warm Air Aloft. A trough, meaning like a valley, a trough of warm air aloft above. And the reason why the Canadian tendency is to go with the trowel is because, as I was mentioning before, this intersection between the cold front and the warm front happens on an ongoing basis, and therefore it continues to develop. The occluded front shows where it first started, and the trough shows where it is currently, as I describe in the captured lecture, and as you'll see in the textbook. Basically, these two fronts, which are two planar surfaces, they kind of, they intersect at some angle, and the trough is that angle, that line of intersection, okay? And it further gets projected back down onto the surface. So this is a so-called surface analysis. It's an analysis of what would be observed at the surface. Okay, so I think I've probably said all of the points I wanted to raise here. There is a tremendous amount of detail, obviously, and it's going to take you a little bit of time to work through this. One of the ways that I think will help you to work through it is if you actually start working with real data. And so I'm going to have you work on assignment 3 with real data from Environment Canada, and I'm going to show you the surface analysis charts. So these are, again, surface analyses. These are mean sea level charts. They are, you'll see that there is both a preliminary analysis. So this is pretty much just the observables, right? So when you look here, and just to kind of help orient you, I wonder if I've got any cool tools here. I think I do. A drawing tool. Let's see if this works. Okay, so it's kind of obscured, but the Toronto area, and that's a terrible color. Can I change the color? Sorry, obviously don't. Oh, there we go. Okay. Roughly speaking, there's the Toronto area, okay? Because I can just make out the outline of Lake Ontario here. Here's Lake Erie, Lake Huron, etc. So what we are looking at here is pretty much the raw data, okay? So you can see data from individual weather stations, such as this one up here, with air temperature and dew point and various. This is actually the wind direction here given as a numeric value, and this is likely the last two digits of the pressure. So this is kind of this is what Environment Canada calls a preliminary analysis, and if I show you then, oh, now I don't know how to get rid of all this non-annotation here. Kind of a rookie with this stuff. I do apologize for that. I guess I can always erase it. There we go. clean things up a bit. Okay, so let me also show you what a surface analysis looks like. So the first thing that's important about the surface analysis is the date and the time. Okay, so down here in the very bottom, you'll see that there is a date. So this is current as of today, and then the time here is given in UTC. Of course, right? Why would anything be nice and simple for you? So this is at the convention is, you'll see 0, 0, 0, 0, 6, 1, 2, and 18. So this is at basically midnight, or sort of just basically the start of today, UTC time. So to get the equivalent time in Toronto, you would need to subtract 4 hours. Okay, remember that we are on EDT currently. So we take the UTC time and take off 4 hours to get the Toronto time. So this is actually, from the Toronto perspective, this is actually yesterday. And in fact, for that reason, maybe what I'll do is I'll get one that's at least early today. So here is 6Z. So that's UTC time of 6 a.m. Take 4 hours off that. So that's 2 a.m. this morning, Toronto time. Okay, this is our surface analysis. And you can see here that we have a very busy, detailed map. Now, what's kind of great about cyclones is there's pretty much always something going on. Let me just pick one that's kind of as clean as possible. So I'll go ahead and pick this example over here. And let me get myself a my draw again. So let's focus in on perhaps this one right here. So here's our warm front, and here is our cold front. And you can see that there is a central region of low pressure that has been indicated here. So this is an example of a cyclone. Over here, we have Newfoundland is this. Still getting used to this tool, and do apologize. Newfoundland's down here. After a while, you get better at kind of identifying things on the map. Here's the center of the cyclone. So this is a cyclone that's currently out over the Atlantic Ocean. And you can see, as I said, the warm front and let me do this in slightly more useful colors. Here's the cold front, etc. And then just to complete the example, we can go over here to this this other cyclone, and you can see the trowel that's indicated here on this cyclone. That's that trough of warm air aloft. Okay, so it is possible to, obviously the real world is always more complicated than that which we see in our textbooks. There's, a tremendous amount of activity over North America at any given time. Now, it's an interesting time in the Toronto area because we are expecting some precipitation today. And actually, here is, let me just do some erasing. We have right here, we have a weather system that, so let's have a look. Here's Toronto area right here. And we are expecting some precipitation. So even as early as 2 a.m. this morning, there was a warm front that was starting to move into our area, and here's its cold front here. So again, to you know, to reiterate, this is all very very practical stuff. So just to kind of use this example a little bit more, and make the color coding is a little bit more appropriate. So here is our cold front right here. So cold air is behind the cold front, relatively speaking. And over here, we have our warm front. So this is the warm sector here, in between two fronts, as it were. This is where we have the warm air. So warm sector, cold sector. We could certainly drill in and look at some of the additional details. Let me see if there's anything else I can point out to here. There is actually. Let's get rid of some of this scribbling. And let me just go ahead and focus in on this system here again. So the center of this cyclone here is currently, or not currently, but at the time that this surface analysis was produced, the center of this cyclone is at this enclosed kind of X that's also being circled. Now, even though this is a peculiar projection, we can actually state the latitude and the longitude of this particular system. So what you are looking at here is the 40 degrees circle of latitude here, as pathetically as I've managed to kind of draw it. So here's 40 degrees north. That would make this 50 degrees north. 60 degrees north is right here. You can almost see it. Okay, so the latitude of the center of this cyclone is currently at about, if this is 40, this is maybe, roughly 48, 49 degrees north. And then in terms of longitude, we have meridians of longitude that cut through here. So this is actually, so in fact, out here, north looks like this. Okay, so north is heading up towards, here is the North Pole from a geographic perspective. So we have a couple of meridians of longitude here, and I'm looking for a value. That looks like, it looks like 50, but I'm wondering if it needs to be more like, there's 140. Well, maybe it is 50. So that looks like it's probably, yeah, that's right. There's 30 there. It can be quite challenging. It's a little bit of an eye chart to find these things. And you're even, I'm seeing it on a decent sized screen directly. You may be looking at this on some other device and it's kind of hard to see. You definitely want to get yourself a copy of this and be able to mark it up. So here's 30 degrees west longitude, 40 degrees west longitude, 50 degrees west longitude. This system is around here, so it's almost all the way to 50. Again, this is probably about 38. I'm going to say about, sorry, 48 west longitude. We can actually specify the latitude and longitude of one of these cyclones as defined by the location of the its central region of low pressure. Okay, so that's something you'll be asked to do on the assignment. You'll also be asked to state the pressure for the center of the cyclone, and that's this big number that is shown here. This is 1006 hectopascals. So that's the current value for the pressure at the center of the cyclone. Now, what's also kind of interesting is that previously, so this is where the cyclone is currently, right where the X, the circled X is. This dot here is where the cyclone was 6 hours ago. So basically, I think this one was 6 UTC today. So this would have been at 0 UTC today from a UTC perspective. And we only show the last 2 digits here. So what this is saying is that 6 hours earlier, the value of at the center of the cyclone was 1,008 hectopascals. 12 hours ago, it was 1,009. And I think that 12 is associated here. 18 hours ago, it was more like 1,000 and 1,012. So over the past 18 hours, the pressure at the center of this cyclone has actually been decreasing. And that tells us that the cyclone is intensifying in terms of its strength. So again, there's there's a wealth of information that can be gleaned from these surface analyses. So if I go over here back to my my slides, this is the kind of thing I'll have you do on the assignment, is fill in a table like this. So we've already talked about a lot of these points here: the date, the time, you convert that to local time, the observed pressure at the center of the cyclone, the location of it in terms of latitude and longitude, the relevant types of fronts. And there was a great question a little earlier. I do apologize, I didn't get to it yet. The question was about the other type of front that was actually shown on this diagram here. That's the front that's labeled AB. It's a so-called stationary front. And this is where 2 air masses have met. So we've got the colder air to kind of the north and east here, and the warmer air more towards, or in this case, maritime polar air towards the south. So this is an interesting situation, the so-called stationary front, and the air masses, because quite often what happens is along a stationary front, a cyclone can actually start to develop. So this is indicating a place where air masses have met, but otherwise there's really not a lot of other things going on. So you've met all the basically there are 4 different types of fronts that are shown here. And so that's all good. So I've talked about the different types of fronts. I've said a little bit about the fact that fronts move. We've talked about the sectors, the fact that temperature are different in the various sectors, winds are different, wind directions are different in each of the sectors. We've said a little bit about air masses. Let's talk a little bit about clouds. Now, I'm not going to have the time to go through this in detail. Again, refer to the captured lectures and the textbook. This is a cold front, and what we tend to find is that vertically developed clouds are associated with cold fronts. And you know, you won't see that. You may be able to glean that by looking at all, you know, some of the data that's coming from the individual weather stations, but I typically have you just kind of make educated guesses about that. What's critical about the clouds associated with cold fronts, in addition to the fact that they are vertically developed, is that they tend to be behind the cold front. They kind of exist right pretty close to the boundary of the cold front. Now, when it comes to warm fronts, it's very different to talk about other differences in scale and so on. Warm fronts tend to be very gently sloping, and they tend to have stratiform clouds associated with them. So this precipitation producing cloud here is a nimbostratus cloud. This is just a stratus cloud. Stratus clouds, remember, are the layered clouds. So the warm fronts tend to produce, you know, very sort of broad features. So This can, of course, be linked directly to precipitation. So when we are experiencing precipitation, if it's a thunderstorm, then it's quite likely that there's a cold front and a thunderstorm that is being developed here. That's not to suggest that thunderstorms require cyclone development, as you'll see when we get into the next week's material on thunderstorms. It's not an exclusive requirement, it's a common requirement. The so again, just to kind of link in the some of the characteristics. So as I've shown elsewhere, when you have vertically developed clouds, you have precipitation that's focused over a relatively smallish area. This might be a 1 to 3 kilometer diameter, cumulonimbus style of cloud, but you can get extremely intense precipitation that doesn't last very long. When it comes to the stratiform style, you can see here that the area that gets covered can be very substantial, and the precipitation persists for quite a long period of time, but it tends to be fairly, low rain rates, not as intense. So that speaks to the cloud and precipitation. So as far as we're concerned, these are the associations between clouds and fronts, these two diagrams here. And again, I do talk about this in much more detail in some of the captured lectures, and you'll certainly see more detail on this in the textbook too. The cyclones, such as this one, actually go through a 6-phase life cycle. Okay, so again, something that is spoken about or discussed in those other resources that I've referred to. So one of the things I like to have you do is to identify which phase of its life cycle the cyclone appears to be in. Now, I've said a little bit about the intensity of the cyclone. The lower the lower value of pressure, the more intense the system. This is the same kind of concept that applies to hurricanes. So you may hear people referring to the intensity of hurricane and speaking about its central pressure. The lower the pressure in the eye of the hurricane, the more intense that cyclone is. So something to be considered. And I think I just alluded to this, but basically these weather systems, as they make their way across North America, they tend to follow a path that is predetermined by the path of the jet stream. So if I was to grab a jet stream resource here, let's see if we can find something fairly quickly. This is usually a good one. So this is the Weather Underground, and unfortunately the jet stream is not cooperating very well today. You can see it here, and usually there we go. So that's a little animation. You're looking at again constant geopotential height contours. So these are the height of a particular pressure surface. For the jet stream, we tend to look towards the top of the troposphere, and so quite often values of the 250 hectopascal contour. So that's just one example of it. You can also get it from the Environment Canada data here. So for example, here is it's let me get my handy dandy marker going again. Where did it go? Really am not very good with this. Okay, So here is an example of the jet stream over here. It's not particularly pronounced today. You can kind of see it elsewhere too. Again, get a sense as to just how wavy it can be. And so there's other information that I do want to draw your attention to on these maps. So this one is a 250 hectopascal map analysis. We'll quite likely include that in our consideration. But the one that we've been talking about a fair bit is also the 500 hectopascal the height of the 500 hectopascal surface. So this is a so-called upper air analysis, and again the Great Lakes are down. Let's see if I can see. We've got Florida here, Hudson Bay. Yeah, there's Superior, and Lake Ontario is right around here, I believe. So this is, as I say, this is an example of an upper level surface here. And the important thing here is that when you see a bend in this 500 hectopascal, the height of the 500 hectopascal surface, it looks kind of like this. A bend that is kind of pointing towards the north here. What that is illustrating is that we have what is called upper level ridge of that surface, which means that we basically have a high pressure aloft situation. And why this matters is because, as I'm going to quickly show, because we are completely running out of time, I'm going to show from here. What matters here is in order for a healthy cyclone to develop and continue to strengthen. So the cyclone's shown over here on the left. And what you really need is to set up a circulation. So there needs to be coordination between what's happening down here at the surface and what's happening up here aloft. So an upper level high, such as what I just showed you, means that we have a region of divergence aloft. If that kind of lines up with a region of convergence down here at the surface, then we have the ability to produce a circulation. Okay, so it's a complex looking circulation. Air spirals into the center of the low pressure system of the cyclone over here on the left, right? It's got a fairly complex trajectory. So the low pressure system represents a region of convergence. The air rises there and then diverges aloft. And it, of course, is linked and coordinated with other regions, in this case, another region of high pressure over here. So there's just a wealth of information that comes from these diagrams. Perhaps I'll just quickly also talk about winds. So let me find a decent surface analysis here. This will serve our purposes. And this should work fine over here. The hardest part about these is, as you can probably tell, is trying to, trying to kind of isolate in on the feature of interest and kind of separate it out from all of the other background. So let me point out here, so let's focus in on this weather station right here. Okay, so here is the wind at this weather station here. Now, and actually I've gone and picked a fairly complicated one, and I tell you what, this will be fine. This will be all right. We can make this work. So the first thing I'm going to do is I'm going to indicate here. So this is what's called the resulting wind. This is the actual wind that is blowing here. So again, if you're out in the ocean in this particular case, we've got Vancouver Island is over here. So this is off the west coast of North America. So if you're actually here on this weather station, and you stand and face the wind is basically coming from the west. Now it's coming from the west because this is your relative indication of north over here, okay? And this is a meridian of longitude. And then here is the east-west reference. This is a part of a great circle of latitude here. So just to kind of help orient you. So first of all, there's the notion of the pressure gradient force. So let's kind of forget about these high pressure systems out here. I mean, they're kind of going to be fine and factored into our analysis here. But here is suppose that this weather station is being it's providing data that is kind of relating to primarily this low pressure system over here. What we would find is that the pressure gradient force will be in the direction of that low pressure system, okay? And this is, my goodness, that's just awful. Let me, we'll definitely have to do a retake on that. Let's try it with a finer pen. So this is supposed to be PGF. Okay, so this is our pressure gradient force. So basically it's pointing in the direction of the low pressure center. It's going from high pressure to lower pressure. So that is our pressure gradient force. There is of course the Coriolis force. And in the Northern Hemisphere, the Coriolis force always tends to be in an opposite sense to the pressure gradient force, and it's always to the right in the Northern Hemisphere. So again, if you're kind of standing at this weather station, this is off to your right. So the Coriolis force, so the pressure gradient force is what kind of guides the strength of the wind. It's based on the difference in pressure. The Coriolis force just changes the direction of wind. So the Coriolis force here would be pointing. Sorry, I never actually said this. The pressure gradient force is pretty much pointing due north. The Coriolis force, or if you were to stand here, and again, you can use different way, you can convey direction however you want to here. The Coriolis force is pointing towards the north, towards the center of the low pressure system. Coriolis force is pointing in the opposite direction, towards the south. The wind is basically blowing more or less in this direction, so from the west or towards the east. This is resultant wind. Okay, the only other consideration here is the force due to friction. And the force due to friction always is in the opposite sense of the resultant wind. So I'd drawn that perfectly. These two would be essentially 180 degrees different. So the force due to friction is coming from the east, or opposes the speed of the wind towards the west here, and it tends to slow down the wind. And it is in fact the reason why, as winds enter into these low pressure systems, they need to be they cross isobars, and there is some curvature. So I think I've managed to cover most of the points. There is a lot of information here. If you're feeling a little bit overwhelmed, that's almost certainly to be expected. There is a wealth of information, as I say, and it's going to take a little bit of time for you to work through this. So we have now, we've spoken about the surface winds, we've spoken about the surface aloft interactions. Geostrophy is that balance that exists when the Coriolis force and the pressure gradient are directed in opposite sense and equal in magnitude or size. And you see that on the upper air maps where the wind is essentially blowing parallel to the constant height contours. More on that when we look at the assignment in some more detail. And I think I've spoken about a lot of these other things. So there we go. So I realize I'm a little bit over time here. Any questions? I think what I'll be doing on the assignment is having you look at one or more surface analyses, and probably linking with some of the upper air analyses to help develop a broader understanding of what's going on. I should also mention that I had intended to talk about radar. So when you see on a radar map, you know, the various features and everything, they probably look a little bit, you know, the patterns of precipitation may at first appear to be fairly, you know, perhaps random. But in fact, when you start looking at some of these details, and I should really say what I'm doing here is I'm clicking on certain, I wanted to keep up the radar map, but I also, one of the reasons I really like the Wonder Map is because it gives you the ability to turn on fronts. Okay, so now that we've got our fronts on here, let's see if we can't get rid of, there we go, managed to get rid of it. And then I want to zoom out a bit here. So this is, of course, a whole lot easier to understand. Here's Toronto. This is a warm front here, you know, and as I said, we're getting some interesting precipitation. One of the toughest things, of course, about working with real data is the real world is a whole lot more complicated. So here's kind of a peculiar warm front that is kind of the city. So we're the warm front precipitation is up over this peninsula that's kind of at the top of the state of Michigan. Yeah, of course, just when I decide I want to try and show you some of this stuff, I'm trying to look for more classic cyclone. That's not a bad one. Warm front here, cold front here. Up here, this is a big kind of hooked looking occluded front. Anyway, lots of variety here. Okay, here's a simpler system up here over Hudson. You can see it here. So we've got a trailing cold front here. So the cold air mass is out here towards the back. This is the warm center that's in here, the warm sector that's in here, and the leading warm front. So the warm air is out ahead here. Sorry, the warm front is, the warm air is here, and you'd have a sloping upwards slope here. So wherever is out underneath is likely a colder air mass. So any questions on this material? This is really important material. As I say, it will be the subject of the next assignment, which I'll try and get out to you as quickly as I can. And it's quite like, well, it's definite that this material will factor into your final exam. So you can be expected to, you know, be asked to work with this kind of data, these kinds of questions. So as I say, there is a lot here. Understanding weather maps is anything but trivial. You may have seen maps like this in the past on a weather app or through some kind of a service in a newspaper, on a television screen, the Weather Channel, what have you. It takes a lot to unpack all of the details here. So it takes some time. And again, the best advice that I can give you is that there is no shortcut here. You just need to engage with this material. Start working with this when I hand out the assignment. Go through the textbook or the lecture captures or both, whatever's been working for you. And then if you engage with it in earnest yourself, you can still collaborate with people on the assignment, of course. I encourage you to do that. That's the way to kind of to work through this and to learn more about this and be able to prepare yourself so that you can complete the assignment and also prepare for the exam. And I think with that, I'm 15 minutes past. Last call for questions, otherwise we can wrap this up, and hope everybody will have a great day. All right, everyone. I hope you found this material interesting. I think this is some of the most useful, practical material that you'll learn from the course, and should give you some lasting value. I've given a very biased North American perspective to the treatment today, but most of what I have said will apply wherever you happen to live or be spending time these days on the planet. So yes, thank you very much. Happy day to you too. Happy day, happy evening, happy afternoon, and we'll see you next time. Take care, everybody.